All right, welcome back to Physics 221. We're discussing special relativity. So last time we learned about this velocity addition rule. So this is the speed of the reference frame that's moving relative to us. This is the speed of the object in that reference frame. This is what we would measure. So here's just a simple example that we talked about last time. So here's us. So we're just sitting still, wasting time on the road. Here's a car going that way, 60 miles an hour. In the car, there's a guy who throws a baseball 100 miles an hour. We're ignoring air resistance. So what would we measure? What would we measure for the speed of the ball? Well, it's simple. We would just take the speed of the car plus the speed of the ball. So we get 160 miles an hour. So that's called the Galilean velocity addition rule. And it works great for most things. All right, so then I think this is where I stopped, but let's go over it again. You ate Wheaties for breakfast today, a lot of Wheaties. You're late for class, so you're running forward at 100,000 kilometers per second relative to the ground. A person standing still behind you shoots a light wave towards you at 300,000 kilometers per second. A person standing still in front of you shoots a light wave toward you at 300,000 kilometers per second. Now here's the important thing. According to Galilean relativity, what speed do the light waves approach you? So here's you, and then there's a person, and again, you're running forward, 100,000 kilometers per second. So then there's a guy in back of you, shoots a light wave, 300,000 kilometers per second. And there's a guy over here, same thing, 300,000. All right, so the question is, according to Galilean relativity, how fast do these light waves approach you? So we discussed this last time. So you're going 100,000 this way, this is going 300,000 that way. So this one, according to Galileo, would appear to be going at 200,000 kilometers per second. And this one would be 400,000. Okay, so that's just review. We explained it last time. And, all right, now, so that's according to Galilean. However, let's do the experiment now. Let's really do the experiment. Forget about the Galilean velocity addition equation. Let's actually do it. So at what speed do the light waves actually approach you? Believe it or not, 300,000 kilometers per second. So this one would approach you at 300,000 kilometers per second. This one would approach you at 300,000 kilometers per second. And if that doesn't blow your mind, you're either not understanding or you've had this before. So this is what we're really saying. So let's say this is us. We're sitting on the ground. Here's a train moving to the right. I don't care how fast. Here's a runner in a train moving to the right. I don't care how fast. The runner is holding a flashlight. The flashlight is turned on. So of course the light coming out of the flashlight travels at the speed of light. So the data indicates that if the runner were going to measure the speed of light coming out of the flashlight, he'd measure the speed of light. That kind of makes sense, right? No kidding. However, the data also indicates that the stationary observer also measures the speed of light to be the speed of light. What does that say? That means that the speed of the railroad train, the train, is irrelevant. It means that the speed of the runner is irrelevant. It means that everybody measures the speed of light to be the speed of light. Doesn't matter how fast the source of light is going, like a rocket or a car or something like that. It doesn't matter how fast the person measuring the speed of light is going, the receiver. Everybody measures the speed of light to be the speed of light. And again, I hope you understand that that's totally insane, right? That's totally crazy. But yet, that's what the data indicate. And this is physics, so you have to go what the data says. All right. Now, we have to explain this. And this is tough, what we're going to do right now. And a lot of students completely missed the point here. So please really, really pay attention. because it's going to set the stage for the entire chapter. I guess that's one thing about having a video. You can just keep replaying it, right? All right, so we have to explain these observations. So here we go. Mathematically. All right, so here, as we've seen before, are the Galilean transformation equations. So here's the position, then we take the derivative, and we get the velocity. And don't forget, the v is the velocity of the reference frame. The u's are the velocities on the object in the reference frame. Okay, so here we go, right? So here's the Galilean velocity addition or subtraction, whatever you want to call them, equations. Now, if frame S is moving relative to frame S, right? I mean, that's our supposition. That's what we started from, right? We're always having frame S prime move relative to frame S. Well, if that's the case, and again, the velocity of S prime is v. So therefore, according to these equations, this does certainly not equal to that. I mean, no kidding. So that sort of makes sense, right? So that's what Galileo says. However, okay, and so what does that mean? So if ux is not equal to ux prime, that means delta x over delta t, or dx dt, is not equal to delta x prime over delta t, or dx prime over dt. So that's not a surprise. However, what did we see with light? With light, it turns out that everybody measures the same speed. So ux equals ux prime. And what does that mean? It means delta x over delta t equals delta x prime over delta t, right? That's just the definition of velocity. Oh my gosh. Well, how can that be? I mean, how can it be? I mean, look. Well, here. Delta, so here's delta x. Here's delta x prime. So come on. They're certainly not the same, right? So x is not equal to x prime, or delta x is not equal to delta x prime, right? So these two, this is not equal to that, but yet this fraction equals this fraction. Well, just stop for a minute and think. How can this equal that if the numerators are different? What's the only way you can answer that question? So just think about it. Pause your video and think about it. All right, I think you have to admit the only way that this velocity can equal this velocity, if this distance is different than this distance, is if the times are unequal. It's the only way, right? The only way you can get that. So this time can't be equal to that time. Now, what does that mean? It means that people in different reference frames, when they time the same event, they're going to get different answers. So that means that time is relative. Is this marker large or small? Well, it's large compared to an atom. It's small compared to the sun, because size is relative. So what we just proved is that time is relative. There's no such thing as absolute time. So this is the time that we would measure in our reference frame. This is the time that somebody in a moving reference frame would measure. They're different. So that's what we talk about. Time is relative. And later on, we're going to figure out the equation, how this relates to that. But now we're just talking about the concepts. Yeah, all right. So the time measured for the same event in one reference frame is not equal to the time measured for the same event in another reference frame. Time is relative. And I hope you appreciate this. All right, so we'll get back to that, don't worry. But before we do that, we need to, remember I told you about this last time? Time is relative. There's no such thing as absolute time. And we just proved it. Okay, now we want to go on a different tangent, whatever. but we'll come back to the time, I promise. So we want to talk about events and space-time coordinates. And these are just fundamental to relativity. So an event has space-time coordinates x, y, z, t in frame S, and different space-time coordinates x prime, y prime, z prime, t prime in frame S prime. Okay, so that's the thing, right? When we talk about space-time, it's just not where it happens. It's also when it happens. And again, remember, look what this is saying. I mean, it's obvious that the x and the y and the z will be different, but now we're saying that the times are different as well, because time is relative. Okay, so here we go. So what's an event? Well, I'm just going to give you the answer, all right? So an event is what really, really happens, okay? So an event has a unique set of space-time coordinates in every reference frame. So this is where it actually happens, when it actually happens. Now, here's the important thing. Number 2 is false. Okay, number 2 says an event is our perception. That's false. It's totally false. And let me kind of explain that. Okay, so here's a photograph of the sun. I think it's X-ray light, and it's certainly not to scale, right? Because it's much, much larger than that. Okay, so go outside. Well, don't actually do this. Just ask yourself this question. How do you know the sun is up there in the sky right now? How do you know? How do you know it's in its normal location in the sky right now? Well, the answer is you don't. You don't know, because the sun is so far away, it takes light, traveling at the speed of light, 8.3 minutes to go from the sun to the earth. So that means when you look at the sun, which you're not supposed to do because you can wreck your eyes, when you look at the sun with proper filters, what you're seeing is what the sun looked like 8.3 minutes ago. For all you know, it could be gone, all right? So that's the thing, okay? That's the whole thing with reality, with an event and a perception. You know, we look at the sun and we think, yeah, it's right there. But that's wrong. We're seeing what it looked like in the past. Okay, so that's hopefully clear. All right, so here's a carpenter is working on a house 2 blocks away. You notice a slight delay between seeing the carpenter's hammer hit the nail and hearing the blow. At what time does the event hammer hits the nail occur? All right, so everybody pause your video and figure it out. All right, we're back. Okay, so now, you know, there's 2 things here, right? You see something, and that's dealing with the speed of light. You hear something, and that's dealing with the speed of sound. Speed of light is, so the speed of light is 3 times 10 to the 8 meters per second. Incredibly fast. Speed of sound is incredibly slow. Compared to that anyway, 343 meters per second. All right? Okay, so what's the answer? Okay, right? And so the event hammer hits the nail occurs slightly before you see it. Well, why is that? Well, think about it. So here's I'm not going to draw it. Here's the guy hitting the nail, okay? All right? And then here's you. Well, you know, it takes time, right, for that light to travel from the hammer to you. It doesn't take very long at this speed, right? But it takes a little bit of time. So by the time you see it, there's been a little bit of a delay. So that's why the event, the actual hammer hitting the nail, occurs just a little bit before you see it. Okay? So we're trying to get the idea across that when something happens, the event is not the same thing as when it's perceived by us. Okay, we have more of these questions for you because you have to understand them to make any progress. Ann and Bill are standing 1,200 meters apart, right? 1,200 meters apart, are facing each other. A firecracker explodes 900 meters from Ann, and she sees a light flash at t equals 5 microseconds. All right, that's when she perceives it. Now the question is, when did the explosion occur? Now here's something that you want to use to answer these questions. So the speed of light is 300 meters per microsecond. So everybody pause your video and figure it out. All right. Well, let's see. How long does the light take to travel 900 meters? Well, according to this, 3 seconds, right? 900 meters, and it goes 300 meters per microsecond, so 3 microseconds. I hope I said that. Okay, so it takes 3 microseconds to travel from here to here. Now she said she saw it at 5 microseconds, so when did it actually occur? At 2 microseconds, all right? It took 3 microseconds to go this far. She said it occurred at 5, so 5 minus 3 is 2. Okay, number 2, are seeing the flash and the firecracker explodes the same event? No, right? Absolutely not. An event is when it actually occurs, not when we perceive it. Okay, so if not, which is the more significant? Well, when it explodes, right? Because that's what we mean by the event, when something actually occurs. Okay, Bill. What time does Bill see the flash? Pause your video and figure it out. Okay, so we're back. Okay, so the explosion actually occurred at 2 microseconds. T equals 2 microseconds. Now, this is 300 meters, so it will take 1 microsecond to reach Bill. So if the firecracker exploded at 2 microseconds, and it took a microsecond to reach him, therefore, Bill sees it at 3 microseconds. Make sure you understand all these. Okay, let's do some more. Ann and Bill are still standing 1,200 meters apart and are facing each other. Firecrackers explode 300 meters away from the front and back of Bill. And Bill, using an extra set of eyes in the back of his head, sees the 2 flashes at the same time. That's the important thing. So Bill, again, this is the same distance as this. Bill sees the explosions at the same time. So according to Bill, were the 2 explosions simultaneous? So pause your videos and figure it out. Okay, well, according to Bill, the distances are the same, the times are the same, so that's what we mean by the speeds are, okay, the distances are the same, the speeds are the same, the times are the same. Therefore, according to Bill, the explosions were simultaneous. That means that they happened at the same time. According to Ann, were the 2 explosions simultaneous? And this is very important. Ann is very intelligent. Okay, so according to Ann, were they simultaneous? Now remember, Bill says they were simultaneous. That means that the times were exactly the same. Now, it's true that his perception was the same, but more fundamentally important, he deducted correctly that they were simultaneous, that they happened at the same time. So Ann, being a genius, right, she says, well, you know, if they're simultaneous, right? Because they're both in the same reference frame, then they're not moving relative to one another, so they're simultaneous, as simple as that. All right, now we're going to keep going. Ann and Bill are still sitting 1,200 meters apart, facing each other. Again, firecrackers explode 300 meters away from the front and back of Bill. Now here's a little bit of a switcheroo. Ann sees the 2 flashes at the same time. Ann and Bill are both very intelligent. According to Ann, were the 2 equations simultaneous? Now look at, well, pause your video, you figure it out. Okay, we're back. she sees the two flashes at the same time. Now this one travels less distance than this one. So if she sees them at the same time, there's no way they can be simultaneous. So Anne says absolutely no. All right. If they occurred at the same time, she would have detected this one before that one, right? Because it's less distance to travel. Now, remember, they're both intelligent. So Anne says they are not simultaneous. Anne and Bill share the same reference frame. They're not moving relative to one another. So according to Bill, were they simultaneous? So pause your video and figure it out. I hope you know the answer. Absolutely not. Absolutely not. Okay, so what's the moral of the story? Number one, the perception of an event is not the event, right? I mean, think about it. A photon leaves the sun. Now, how long does it take to reach us? 8.3 minutes, right? So we see the photon, we think, bingo, you know. But, I mean, we look at the sun, right? And we think, you know, we're seeing what's happening right now. We're not. We're seeing in the past, 8.3 minutes ago. So the perception is not the event. And here, all experimenters in the same reference frame agree as to whether or not two events are simultaneous. Now, in practice, experimenters must calculate the time delay effects, you know, to turn their perceptions into measurements. And we saw that. But we're assuming that the experimenters are smart enough to do that. All right, let's talk about the speed of light being constant. Everybody measures the speed of light. Let's talk about that now. We saw this a few minutes ago, right? Again, I don't care how fast the train moves to the right. I don't care how fast the runner moves to the right. The runner is going to measure the speed of light to be the speed of light. This guy is going to measure the speed of light to be the speed of light, which is really weird. So we have to explain that. All right, now don't have a heart attack about this. This is physics 220. So these are the Maxwell's equations that explain everything there is to know about classical electricity and magnetism. And these equations make a prediction. Here's the prediction. All electromagnetic waves, in other words, light waves, radio, radar, microwave, X-ray, infrared, visible, ultraviolet, I just said X-ray, gamma ray, everything travel at the speed of light. So it doesn't matter what kind of light it is, all types of light travel at the speed of light. And here's the speed of light, which I showed you before, 3 times 10 to the 8th meters per second. And for the Americans, 186,000 miles a second, incredibly fast. So that's a prediction from Maxwell's equations. And you know, Maxwell's equations work, all right? Maxwell's equations work. Now, okay, so, you know, and notice there's no mention of reference frame. Remember at the very beginning, I stood here and I said, am I moving? And the answer to that question was improper question or something like that. I might not be moving relative to this room, but I'm certainly moving relative to the sun and so forth. So we talked about how, you know, you have to, when you ask a question like that, you have to state the reference frame. But here there's no reference frame. It just says everybody measures the speed of light to be c. Everybody. We don't care what reference frame you're in. Everybody measures the speed of light to be the speed of light. That's what the Maxwell's equations say. All right, so that's one thing. Now here's another one. So this is a logical argument from Einstein. Make sure you understand this, just the flow, the logic, because it's tight. It's a good argument. So Einstein says, okay, there's something called the principle of relativity, which we've discussed, which says that the laws of physics, mechanics, and electromagnetism are the same in all inertial reference frames. Okay. Well, all right, so we know that. That's true. And that agrees with data, you know. Laws of physics are all the same in all inertial reference frames. So if you go in a jet, the jet's moving at constant speed, constant direction. You turn on a computer, you know, it works the same. You throw a ball up, it works the same as here, you know, not a big deal. Well, here's a law. Here's a law of physics. A law of physics from electromagnetism is that c is constant, right? There it is. That's a law, you know. The speed of light is constant. That's what Maxwell says. So here's a law. The speed of light is constant. Well, therefore, put this together with this. Therefore, the speed of light has to be constant in all inertial reference frames. I mean, it's a pretty good logical argument. It doesn't make any sense, but it makes logical sense, you know. Hope you understand that. All right? So just by logic, the speed of light has to be constant in all inertial reference frames. What does that mean? I've already said it a million times, right? Therefore, the speed of light is constant regardless of the observer's motion, regardless of the light source's motion. Everybody measures the speed of light to be the speed of light. So if you ever have a test question, you know, there's a rocket moving some speed towards you or away from you, doesn't matter, and turns on the headlight. What's the speed of light? Speed of light. You don't have to do any thinking. Speed of light. It's always the speed of light. Oh boy. All right, there we go. Third time I've showed you that. Okay, everybody measures the speed of light to be the speed of light. Now, totally insane. Doesn't make a bit of sense, right? But there's data. There's evidence. And I want to review some of that evidence now. So this is Fermilab, where I used to work. This is a particle accelerator. So this is 4 miles in circumference. And so what they do is they get protons in a vacuum tube, and they accelerate them to nearly the speed of light, and then they smash them with stationary particles, or they smash them with particles going in the opposite direction. But that's what a particle accelerator is. Okay, so in other words, this is a great place for doing experiments with relativity, because you can actually have objects that travel nearly the speed of light. I mean, where else can you get something that travels at nearly the speed of light? You know, that's not light. Okay, so, all right, here we go. So first let's talk about a pion. So a pion is just a subatomic particle, not a big deal. And the pions, that's the pion, doesn't last very long, so we say it decays. I guess we should say it dies, but we say it decays in particle physics. So oftentimes the pion decays into 2 photons, where a photon is a particle of light. Okay, wonderful. Now, this is an experiment they did in Geneva, Switzerland, and way back in 1964. So what they did, they accelerated a bunch of pions to nearly the speed of light. I mean, that's pretty close to the speed of light. And then, you know, again, the pions don't last very long. And so here, I'm the pion. Okay, just pretend I'm the pion. Okay, so just pretend I'm the pion and I'm going that way at nearly the speed of light. And when I decay, so as I decay, or when I'm decaying, I emit 2 photons. Okay? Now remember, I mean, I'm going at nearly the speed of light, right? And then I emit a photon that way and that way. I mean, all right, so that's what the experiment was. Now, here's the question. What is the speed of the photon on the left? That's what they wanted to measure. What's the speed of the photon, this guy? Now, let's answer it according to Galileo. All right? What would Galileo say? Well, he would say, let's just say this is the speed of light, all right? So Galileo would say, well, that's the speed of light this way. That's the speed of light that way. So the speed of this, right? So, but remember, this pion was traveling it that way when it emitted this photon going that way. So speed of light minus speed of light is 0, right? That's the Galilean velocity equation. So Galileo would say the speed of this photon, which is emitted from this guy going super fast to the right, would be 0. What would Einstein say? Everybody measures the speed of light to be the speed of light. A photon is light. Okay? So, all right, so Galileo would say 0. That makes sense, right? And then what's the actual result? Speed of light. Now, come on! This is 3 times 10 to the 8th meters per second, or 186,000 miles a second. This is 0. You can't mess up an experiment that badly, right? I mean, what does this indicate? It indicates that Einstein was right. Yeah, this is kind of funny. So in 2011, there was an experiment done over in, I don't remember, Europe somewhere, Italy. And the experimenters were shocked because their data indicated that something had gone faster than the speed of light. And everybody's going, oh my gosh. And the experimenters didn't really believe it. So they gave this big talk, and they said, here's our results. We don't really believe it, but we would certainly appreciate if other groups could help us figure out what went wrong. Because nothing's supposed to go faster than the speed of light. So then, a year later, ta-da, they figured out that there was a problem with the experiment, so life is back to normal. But anyway, let's just review. Okay, so here's a review. So here's the speed of light. I don't care to memorize that. I'll just say 3 times 10 to the 8th meters per second. And they always use a little lowercase c for the speed of light. And this is what some people claim. It maybe means Latin for speed. I don't know. I don't care. But here's the important thing. With respect to what? With respect to any inertial reference frame. So again, that's what we're talking about in special relativity, right? Just inertial reference frames. So everybody in any inertial reference frame, doesn't matter how fast or slow we're going, or what direction, everybody measures the speed of light to be the speed of light. And we'll stop there.